Linear discrimination. In linear discrimination, we assume that instances of a class are linearly separable from instances of other classes. This is a discriminant-based approach that estimates the parameters of the linear discriminant directly from a given labeled sample. Introduction. Remember from the previous chapters that in classification, we defined a set of discriminant functions gj of x, j equals to 1, 2, 3 until k, and then we choose ci if gi of x is equals to the maxima of gj of x, where the maxima is taken among j starting from 1 to k. Previously, when we discussed the methods for classification, we first estimated the prior probabilities p hat of ci and the class likelihood p hat of x conditioning on ci, then used the Bayes' rules to calculate the posterior densities. We then defined the discriminant functions in terms of the posterior. For example, gi of x equals to the log of p hat of ci conditioning on x, and this is called the likelihood-based classification, and we have previously discussed the parametric chapter 5, semi-parametric chapter 7, and the non-parametric chapter 8 approaches to estimating the class likelihoods p of x conditioning on ci. We are now going to discuss discriminant-based classification, where we assume a model directly for the discriminant by passing the estimation of likelihoods or posteriors. The discriminant-based approach, as we also saw for the case of decision trees in chapter 9, makes an assumption on the form of the discriminant between the classes and makes no assumption about or requires no knowledge of the densities. For example, whether they are Gaussian or whether the inputs are correlated and so forth. We defined a model for the discriminant gi of x conditioning on phi, explicitly parameterized with the set of parameters phi, as opposed to a likelihood-based scheme that has implicit parameters in defining the likelihood densities. This is a different inductive Bayes. Instead of making an assumption on the form of the class densities, we make an assumption on the form of the boundaries separating classes. Learning is the optimization of the model parameters phi1, phi to maximize the quality of the separation, that is, the classification accuracy on a given labeled training set. This differs from the likelihood-based methods that search for the parameters that maximize sample likelihoods separately for each class. In the discriminant-based approach, we do not care about correctly estimating the densities inside class regions. All we care about is the correct estimation of the boundaries between the class regions. Those who advocate the discriminant-based approach, for example, Vapnik in 1995, state that estimating the class densities is a harder problem than estimating the class discriminants, and it does not make sense to solve the hard problem to solve an easier problem. This is, of course, true only when the discriminant can be approximated by a simple function. In this chapter, we concern ourselves with the simplest case where the discriminant functions are linear in x, that is gi of x conditioning on wi and wi0 is equals to wi transpose times x plus wi0, which is equals to the summations of wij times xj, where summing j starting from 1 to d, plus wi0. The linear discriminant is used frequently mainly due to its simplicity. Both the space and the time complexities are big O of d. The linear model is easy to understand. The final output is a weighted sum of the input attributes, xj. The magnitude of the weight, wj, shows the importance of xj, and its sign indicates if the effect is positive or negative. Most functions are additive in that the output is the sum of the effects of several attributes, where the weights may be positive, enforcing, or negative, inhibiting. For example, when a customer applies for credit, financial institutions calculate the applicant's credit score that is generally written as a sum of the effects of various attributes. For example, yearly income has a positive effect. Higher incomes increase the score. In many applications, the linear discriminant is also quite accurate. We know, for example, that when classes are Gaussian, with a shared covariance matrix, the optimal discriminant is linear. The linear discriminant, however, can be used even when this assumption does not hold, and the model parameters can be calculated without making any assumptions on the class densities. We should always use the linear discriminant before trying a more complicated model to make sure that the additional complexity is justified. As always, we formulate the problem of finding a linear discriminant function as a search for the parameter values that minimize an error function. In particular, we concentrate on gradient methods for optimizing a criterion function.